Relational model. Tables. Data is organized into tables, where each table contains rows, tuples, of similar data. Set-based operations. Operations on data are performed on entire sets or tables at once, making querying and updating straightforward. SQL, structured query language. Standardization. SQL is a widely accepted language for managing databases, standardized by ENSI and ISO. Descriptive. SQL queries specify what results you want, not how to get them. For example, select name from employee where city equals Kent, retrieves names from the employee table where the city is Kent. Table results. SQL queries always return results in table form, which makes it easy to handle large sets of data with a single command. 3. Procedural languages. Complexity. Procedural languages require users to write detailed instructions on how to retrieve data. This usually involves processing data one record at a time and knowing the database's structure. User effort. Users must manually specify steps and paths for data retrieval, making it more complicated. Ease of use. For end users, SQL is easier for most people to use because it doesn't require in-depth knowledge of the database structure or programming skills. Even occasional users can run queries successfully. Procedural languages. These are more difficult for non-experts as they require understanding the database's layout and writing complex retrieval procedures. Natural language. Modern systems. Some modern databases can be queried using natural language, making it even easier for users to interact with data in a way that feels familiar and intuitive. In summary, SQL makes database queries simpler and more accessible compared to procedural languages, which require more technical knowledge and detailed instructions. Key points. Purpose of databases. Store data centrally, permanently, and in a structured way. Relational Database Management Systems, RDBMS. Integrated system, manages tables consistently. Components. Storage component, stores data, relationships, and system tables, cannot be manipulated by users. Management component, uses SQL for data operations and includes functions for data restoration, protection, and backup. Properties of RDBMS. Model. Relational model with data in tables and defined relationships. Schema. Definitions of tables, attributes, keys, and integrity rules. Language. SQL for data operations, definition, selection, manipulation. Architecture. Data and applications are segregated to ensure data independence. Multi-user operation. Supports simultaneous access by multiple users with transaction management. Consistency assurance. Tools to ensure data integrity. Data security and protection. Mechanisms to guard against destruction, loss, or unauthorized access. Nosql versus RDBMS. Nosql databases partially meet these criteria. RDBMS is preferred for many organizations, but needs to be complemented with Nosql for handling big data or global web application. Definition and scope of big data. Big data refers to large volumes of data that exceed the capacity of conventional software to process. Sources include social media, emails, multimedia archives, search queries, document repositories, sensor data, financial data, traffic data, satellite images, smart meters, e-commerce processes, e-health, and monitoring systems. 3 versus of big data. Volume. Extensive amounts of data, ranging from gigabytes to zettabytes. Variety. Data in various formats, including structured, semi-structured, and unstructured, text, graphics, images, audio, video. Velocity. The need for real-time or high-speed data processing. Gartner's definition. Big data involves high volume, high velocity, and high variety information assets that require innovative processing for better insights and decision-making. Importance for organizations. Companies. Big data helps in generating decision-relevant knowledge for survival and competitive advantage. Governments and NGOs. used in smart city initiatives and sustainable urban development, including mobility, resource management, social networks, and security. Additional versus value. Big data applications should enhance enterprise value, leading to investments in personnel and technology. Veracity addresses data quality and accuracy. Reliable algorithms are needed to evaluate and ensure the validity of data. Challenges: managing the volume, variety, and velocity of data effectively. Ensuring the accuracy and quality of data through appropriate methods and algorithms. Here are the key points from the text. 1. Pre-relational databases. Before TED-COD's relational model, non-relational databases like hierarchical and network models were used. 2. Post-relational development. Even after the introduction of Relational Database Management Systems, RDBMS, non-relational models continued to be used in technical and scientific applications, such as CAD systems, due to challenges in splitting complex technical objects across multiple relational tables. 3. Big data and the Internet. The rise of the Internet and the need for big data management have highlighted the limitations of relational databases, particularly for handling large volumes and varied types of data. 4. Nosql terminology. Nosql refers to non-relational databases that either do not use tables or do not use SQL as their query language. It is often used interchangeably with non-relational. 5. NoSQL demand. NoSQL technologies are favored for big data applications due to their better handling of speed, volume, and variety of data. The term NoSQL can also mean not only SQL, indicating that these systems may use SQL alongside non-relational features. 6. NoSQL structure. NoSQL databases typically use distributed architectures and non-tabular data structures. They support various replication concepts to ensure high availability and fault tolerance. 7. MapReduce. This process involves distributing tasks across multiple nodes to process large data volumes efficiently. It consists of two phases: map, extracting key-value pairs, and reduce, combining partial results. 8. Consistency models. NoSQL databases may offer strong consistency, guaranteeing consistency at all times, or weak consistency, allowing temporary inconsistencies to improve availability and partition tolerance, as per the CAP theorem. 9. NoSQL database characteristics. Model. Non-relational database model. Data. Handles large volumes, flexible structures, and real-time processing. Schema. Not bound by a fixed schema. Architecture. Supports massively scalable applications. Replication. Supports data replication. Consistency. Consistency may be delayed to prioritize availability and partition tolerance. 10. Types of NoSQL databases. Key-value stores. Store data as key-value pairs, e.g., session management in online stores. Document stores. Manage records as documents with self-contained data, e.g., order details with customer profiles. Graph databases. Handle data related to relationships and connections, such as movies and actors. The CAP theorem, formulated by Eric Brewer, states that a distributed database system can only achieve at most 2 out of the following 3 guarantees simultaneously. 1. Consistency. All nodes in the system have the same data at the same time. A read operation will always return the most recent write. 2. Availability. Every request, read or write, receives a response, whether it is the most recent data or not. The system is operational and responsive. 3. Partition tolerance. The system continues to operate despite network partitions, i.e., communication breakdowns between nodes. The system can handle partial network failures and still function. In essence, a distributed database system must choose between consistency and availability, but may sacrifice partition tolerance. Consistency and partition tolerance, but may sacrifice availability. Availability and partition tolerance, but may sacrifice consistency. The CAP theorem implies that no distributed system can simultaneously guarantee all three properties. Systems must balance these aspects based on their specific requirements and use cases. 1. Graph structure and properties. Nodes represent concepts or objects with attributes. Examples include movie, genre, actor, and director. Edges represent relationships between nodes, such as acted_in, has, and directed_by. Edges can also have properties, such as an actor's role in a movie. 2. Manifestation level. Graph database stores concrete values for nodes and edges as separate records, differing from relational databases that use key references. This structure supports efficient network analyses. 3. Graph query language, Cipher. Purpose: a declarative query language for pattern extraction from graph databases. Standardization: ISO plans to develop Cipher into an international standard graph query language, GQL. Basic elements. Match specifies nodes, edges, and search patterns. Where applies conditions to filter results. Return specifies and aggregates desired results. Example queries. Retrieve the year of release for The Matrix. Cipher. Match movie title, The Matrix. Return year. Find the actor who played Neo in The Matrix. Cipher. Match actor acted_in role, Neo movie title, The Matrix. Return a name. 4. Comparisons with SQL. Cipher versus SQL. Cipher is designed for graph traversal and relationship analysis, which SQL struggles with, particularly for recursive searches and graph properties. 5. Graph databases versus relational databases. Graph databases emphasize relationships between nodes and edges, enabling efficient network traversal. Relational databases focus more on structured data in tables with key references. 6. Future directions. Document databases will be discussed as an alternative model for handling structured objects.